All right, kids, time for our very final discussion, discussion 9.3, last discussion of the year. It's all on chemical equilibrium. All right, so let's talk about the first thing, reversible reactions. A reversible reaction is a reaction that can proceed in both directions. So it's just a reversible thing. So one reversible thing is my commute, because I can drive from home and go to work, and the reverse would be go to work to home. So when we have a reversible chemical reaction, we show that in the equation by showing a double-sided arrow. What this essentially means is that our reactants A and B can combine to form products C and D, and we would call that the forward reaction, just because it's following the direction that a chemical equation usually does. We have our reactants on the left and our products on the right. But in a reversible reaction, our products, C and D, can also combine and go back and form A and B. That would be known as the reverse reaction because it's just the opposite of the forward reaction. So now let's go ahead and define what we mean by equilibrium. The word equilibrium essentially means balance. So a system that's in a state of dynamic equilibrium will be in a closed system because the rate of the forward and reverse reactions are equal. And the amounts of the reactants and products stay the same. So this is the definition of equilibrium. A system at equilibrium will have equal rates for the forward and reverse reaction. And because the rates are equal, you'll see the amounts of reactants and products remain constant because A and B are combining to form C and D at exactly the same rate that C and D are combining to form A and B. So every one of those that happens, so you don't see a change. Now, why do we call it dynamic? And equilibrium is referred to as dynamic because the reactions are continuing to occur even though the whole system appears motionless or static. In other words, it appears to us that nothing is happening because the concentrations are remaining constant, but the reactions are actually occurring. We just don't notice that change because they're at equilibrium. So a good analogy is walking up an escalator that's moving down. Now, if you're walking up at exactly the same speed that it's moving down, your position will not change because your upward speed is equal to the downward speed. All right, so let's move right along. Now, at equilibrium, it's important that we separate the words constant and equal because a lot of kids assume they're the same thing. So let's just go ahead and define these terms so you can see that they're not. Constant just means not changing. Equal means two things have the same value. So two things can be constant, but not necessarily equal to one another. And we can see that by looking at these two graphs. But before we do that, let me just remind you of some things we learned in our previous units. So let's assume we have a reversible reaction. I'll just keep it as simple as possible. A plus B in a reversible reaction to make product C. Now, think about baking cookies. Before you combine your ingredients, you haven't made any cookies. So before we combine our reactants, we haven't made any C. So remember from our topic on rate of reaction, high concentration equals high rate. So as the reaction proceeds, the concentration of A and B will decrease over time. Because as these two things combine to form C, C is a unique substance that is a combination of elements A and B, but remember, compounds don't have the same properties as the elements from where they come. So over time, as A and B are consumed, the amount of A and B will decrease. And as the reaction proceeds, as C is formed, its concentration will increase. So over time, what we expect to see is the rate of the forward reaction decrease and the rate of the reverse reaction increase. So let's go back to our graph here. Well, we can see initially the reverse rate is 0 because initially we haven't even mixed our reactants together. And it's not quantified here, but the forward rate will be at its highest point at time equals 0 because the concentration is highest before we mix them. So over time, the rate of the forward reaction decreases as reactants are consumed, and the rate of the reverse reaction increases as products are created. You get to a state of equilibrium when the rates are the same. So this graph down here is just a plot of the amount of reactant over time. So initially we don't have any products because we haven't mixed our reactants together, and we have all reactants. So over time, the amount of reactants decreases and the amount of products increases. Now notice when we get to equilibrium, the amounts don't change, but as you can see in this case, they're not necessarily equal. So just make sure you know the definition for equilibrium. Rates are equal, which means amounts or concentrations are constant. Now you can actually determine experimentally which you will have more of at equilibrium. Here we can see in this graph we have more products than we do reactants, but sometimes you can have more reactants than products. Now in order to determine this, we use what's known as an equilibrium constant expression. So an equilibrium constant expression is just an equation that comes from a balanced chemical equation. All equilibrium constant expressions are denoted with a capital K. So in order to get an equilibrium constant expression, you have to have a balanced chemical equation. Each expression will be K equals, and then your stuff. Notice here, our products are C and D, and the coefficients are L and M. So C raised to the L, D raised to the M, divided by reactants raised to the coefficients. So here are our reactants. So A raised to the J power, B raised to the K power. So these are both products and reactants. So all you got to do is look at the equation, multiply the concentrations of all the products together, and raise them to the power of their coefficients. And divide in our denominator by the concentration of our reactants raised to the power of their coefficients. So take a minute just to look at this equation and see how we turn this equation into our K expression. Now notice here we have concentrations. We can only include things in our expression, in our K equation, that could have a concentration. So pure substances don't have concentrations because when we determine concentration, it's basically the amount of solute to the amount of solvent. So we have to have a mixture. And by definition, things that are pure don't have concentrations. So pure substances in this case will equal liquid or solid. Now you might say, well, gases can be pure substances, but remember that concentration is just the amount of particles per unit volume. So if we, let me just say here, let's say I have one balloon that has 3 gas particles in it, and I take that balloon and squeeze it down to a smaller volume. Now remember, we calculate concentration by the, in this case, moles of gas, you could say, divided by the volume of the whole system. Well, since in each case we have 3 particles, but here we have a greater volume, that means that would increase. All right, so let's go back here to our discussion and see what that looks like. Now, if you see an equation, you'll be given state symbols that'll tell you whether things are solid, liquid, gas, or aqueous. We're only going to include things that are gaseous or aqueous and ignore everything else. All right, so let's go ahead and write a couple of equilibrium constant expressions. You should pause the video at this point, take a minute or two to see if you can write them all on your own, and then I will give you the solutions. All right, so for the first one, very first thing I should check is that everything is fit to go into our K equation. Everything here is a gas, so that all works. If we look at the second one, I have water here as a liquid. Since water is a liquid, we're just going to ignore it. So for the first one, my products are CO2 and H2O. Coefficient in front of CO2 is 3. Coefficient in front of water is 4. If I look at my reactants, the coefficient in front of C3H8, which is propane, is 1, and the coefficient of oxygen is 5. So this K expression will be carbon dioxide cubed times water raised to the 4th power divided by propane to the 1st power times oxygen to the 5th power. Products raised to their coefficients divided by reactants raised to theirs. For the next one, again, we're going to leave out water because it's liquid. Everything else is gas or aqueous, so it can go in. Now, conveniently enough, all the coefficients are 1, so we don't have to worry about adding exponents, but it's just going to be products over reactants. So hydroxide times ammonium divided by ammonia. All right, so we can actually calculate a value for K. To do that, you'll be given some concentrations. All you have to do is write the K expression for the equation, plug in the concentrations, and based on your answer, it'll tell you whether you have more reactants or products at equilibrium. I think I'm going to need another piece of paper here. So in a general sense, a very general sense, each K equation is just products over reactants. So let's consider two situations. One, where we have more products than reactants. So let's just say 4 over 2 equals 2. So if the numerator is bigger, it'd be greater than 1. So now let's look at another one where we have more reactants than products. Well, if I had 2 units of products and 4 units of reactants, that would be equal to 0.5. So we can see whenever we have a simple equation like this, if the numerator is greater than the denominator, you would have an answer greater than 1. And if the numerator is smaller than the denominator, you'll always have a fraction or a number that is less than 1. Well, we see here, if the number is greater than 1, we have more products than reactants, and if the number is less than 1, we have fewer products than reactants. So essentially, let me select the right thing, if the answer you get for K is greater than 1, well, that means you'll have a greater concentration of products at equilibrium. And if it's less than 1, you'll have a greater concentration of reactants. All right, so let's do a little practice. I will show you how this works, and then I'll have you pause the video and do another one. So this example says nitrogen dioxide decomposes at high temperatures according to this equation. Calculate the value of the equilibrium constant. When you see this word equilibrium constant, it's just asking you to calculate K if the equilibrium concentrations are as follows. So we're given the concentrations of our reactants and products. First thing we need is to write the K equation. It'll be NO squared times O2 over NO2 squared. We're given the values for each of those things. Plug the values into the equation you made and solve. Now, 1.4 times 10 to the minus 3 is 0.0014. That's less than 1. So that means we will have more reactants. And the reason why? Because the value is less than 1. All right, so take a moment, pause the video here, and see if you can do exactly the same thing. We're given an equation, we're given the concentrations, and you're asked to calculate K and state whether you will have a greater amount of products or reactants at equilibrium. So pause and go ahead and do that. All right, so just like before, we're going to punch everything into our equation. It's going to be SO3 squared, or create the equation first, divided by SO2 squared times O2. Plug in the values you're given. In this case, you get 115.6. That's much greater than 1, which means your numerator is greater than your denominator, which means you will have more products because the value of K is greater than 1. Okay, so now let's talk about Le Chatelier's principle. So you can actually take a system at equilibrium and tweak it, throw it out of equilibrium. Because for any reaction, the concentrations of reactants and products are always the same at equilibrium. So if you take away or add reactants or products, you throw the system out of equilibrium. Okay, so we're back. Oh, sorry. So you can throw the system out of equilibrium. Now, what Le Chatelier's principle says is that if you have a system at equilibrium and you do something to disrupt that equilibrium, the system will automatically counteract that change and return to a state of equilibrium. So essentially what you're going to be doing here is telling me what you would have to do to get back to equilibrium. So on our slide here we have this equation. Don't worry about what this equation means, but it's a great example of a reversible reaction. So I like to think of equilibrium being like a seesaw. And equilibrium means balance, so at equilibrium, our reactants and products will be balanced. Well, let's consider for a second that I add some reactant, which in this case is that HIN. Think of adding the reactant like adding weight to that reactant side of your seesaw. That's going to cause your seesaw to tilt like this. So Le Chatelier's principle questions ask you, what would we have to do to get back to a state of balance? Well, if it's tilted this way, we would have to add more products, or more products would have to be created. Well, what if we added H plus? Well, H plus is a product, so adding H plus would cause our seesaw to tilt like so. So what would we have to do to get back to equilibrium? We'd have to add more reactants. So think about it kind of like a seesaw. Doing this throws the seesaw out of whack in which way? What do we have to do to get it back to a state of balance? So there's a few different things we can do. Sorry about the bell there. And actually, I'll just write these down on my thing here. We could either, actually, let me do one more example here. Let's say we remove H plus, take it away. Well, that's removing from the products. So that would cause the seesaw to tilt like that. So if you remove products, you have to add more products to bring it back. So there's really three changes we could do. We could change the amounts of reactants and products. We could either add reactants, add products, or take them away. One thing we haven't considered yet, we could change the temperature, and I'll explain that in a second. Or if it's a system of gases, we could change pressure. So let's go ahead and look at all three of those one at a time. Now, the beautiful thing is, when we're doing these Le Chatelier problems, we don't actually have to explain why. It really all has to do with reaction rates, but again, you don't have to explain why. So it becomes something that's very intuitive. If you add more reactant, the system will shift to make more products. Think about it. If you're making cookies, if you add more ingredients, more reactants, you make more products, more cookies. So it's very intuitive. Well, if we're talking about the reverse reaction, if we add more products, well, that's going to cause the reaction to shift to make more reactants. If you remove a product as it's formed, well, if you take something away, we got to make it up, right? So if you take away a product, the reaction will shift to make more products. So the two other factors that can cause a shift, like I mentioned, are temperature and pressure. So let's first look at temperature. Let me actually get another piece of paper, Chip. So remember, from Unit 7, kind of a recent one, that if a reaction is exothermic, that essentially means that for that reaction, heat will be a product of that reaction. And if it's endothermic, then heat will be a reactant in that equation. So increasing temperature is like adding heat. Well, if you add a product, it shifts back toward reactants. If you add a reactant, it shifts toward products. So what we have to do is know that for exothermic, heat is a product, and for endothermic, heat will be a reactant. As long as you understand that, then making the estimate is the same as doing these. Because if you add more reactant, you make more products, and so forth. All right, so if it's an endothermic reaction, heat is a reactant. So adding more heat is like adding more reactant, which will cause a shift toward products. If it's an exothermic reaction, heat is a product, so adding more heat would shift toward reactants. Now, with pressure, this only works with a system of gases. But if you have a system of gases and you squeeze those gases, increase their pressure, the pressure will relieve itself. So pressure always flows from high to low when it's squeezed, and so low to high when it's, unsqueezed. So what you have to do is look at the equation, add up all the coefficients on each side for the things that are gases. Whichever side has a greater total amount of gas will be the, quote, high pressure side. So you have to count the moles of gas on each side. If you increase the pressure, it'll shift to the side with fewer moles of gas from the high to the low. So if you decrease the pressure, it will shift to the side with more moles of gas. So the opposite, the side with less to the side with more. All right, so last thing we could do is use a catalyst. A catalyst does not cause a change in equilibrium. It does make the reaction rates go faster, but it makes the rate, it increases the rate of the forward reaction and the reverse reaction equally. So if they're equal at equilibrium, if they both change equally, they'll still be equal, so it'll still be at equilibrium. So a catalyst does not make a shift. All right, so take a minute, pause the video. Here you're given an equation. It's hard to do a reversible arrow, so you don't see one there, but it's there. Go ahead and see if you can answer these questions. It says, so pause the video and blah, blah, blah. All right, so the first one says, add more nitrogen gas. Nitrogen is a reactant here, and adding more reactant makes more products. If we add more ammonia, ammonia is a product, so adding more ammonia shifts back toward reactants. If we remove ammonia as it's formed, well, then we got to make more, right? So we'll make more products. Now for the pressure. You have to, count. I just had lunch. We got to count the coefficients. Whichever side has the sum of coefficients that's greater, that'll be your high pressure side. So here I have 3 moles of hydrogen and 1 mole of nitrogen, 4 moles in total, and on the product side I only have 2. So if we increase the pressure, it goes from the side with more to the side with fewer, so you'd make more products. Decreasing the pressure would do the opposite. So this is an exothermic reaction. So in an exothermic reaction, remember heat is a product. So if you add more heat, you're adding more products. If you add more products, it shifts back toward reactants. You can all do this. All right, so what you got to know for the Unit 9 test? All the equations. So in topic 9.1, there was just 2. The equation for the calculation of concentration and how we determine changes to solutions when we dilute them. So the dilution equation and the concentration equation. In topic 9.2, we had a few, but these 4 are really all connected together, as hopefully you are seeing. And then we have the equation that shows us the relationship between pH and pOH and our titration equation. And finally, just know how to do these Le Chatelier problems, know how to define dynamic equilibrium, be able to write an equilibrium constant expression, and be able to plug values into it and solve, and based on the value of K, predict whether you will have more products or more reactants at equilibrium. So thank you all so much for watching. Happy studying. Last test of the year, excluding the final. Let's get it.